Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In continuance with the discussion about sampling distribution, in this session we are going to discuss about sampling distribution of variance. As a basic for studying sampling distribution of variance, we have studied chi-square distribution in the previous session. So, the objective of this session is to study in detail about the sampling distributions of variance. Also, a problem is worked out in sampling distribution of variance using the central limit theorem for sample variance. So, first of all, to arrive at sampling distribution of a sample variance S square, we shall discuss the sampling distribution of n minus 1 into S square by sigma square. Already we have seen the chi-square distribution with k degrees of freedom, that is if x is a normal random variable, then Zi will be standard normal random variable with mean 0 and variance and standard deviation 1. Then the summation of the squares of k standard normal random variables becomes chi-square random variable with a k degrees of freedom. This type of discussion we have already done in the previous session. So, in continuance with that, we are going to discuss about sampling distribution of n minus 1 into S square by sigma square. That is to determine the sampling distribution of the sample variance S square. Note that if x1, x2, x3 etc. up to xn are n random variables each with mean mu and standard deviation sigma, then summation xi minus x bar whole square is equal to summation xi minus mu whole square minus n into x bar minus mu whole square. Let us see how this is arrived at. Take summation xi minus x bar whole square, where I is equal to 1 to n. Add and subtract mu. Summation I is equal to 1 to n xi minus mu plus mu minus x bar whole square. This is equal to summation I is equal to 1 to n. Just write it in this format, mu minus of x bar minus mu whole square. Use a minus b whole square formula. So, summation I is equal to 1 to n xi minus mu whole square plus x bar minus mu whole square minus 2 into xi minus mu into x bar minus mu. Okay. This is equal to summation I is equal to 1 to n xi minus mu whole square plus x bar minus mu whole square is actually a constant with respect to the summation. Therefore, since it is added n times, you will have n into x bar minus mu whole square minus 2 x bar minus mu into summation xi minus mu. Okay, where summation is I is equal to 1 to n. Then that becomes n times x bar minus mu, this particular thing. So, that becomes summation I is equal to 1 to n xi minus mu whole square plus n into x bar minus mu whole square minus 2 into x bar minus mu into n into x bar minus mu. Summation xi is equal to n into x bar, and summation xi minus mu will be equal to summation xi minus summation mu, which is n x bar minus summation mu is n mu, therefore n into x bar minus mu. Okay. So, that becomes equal to summation I is equal to 1 to n xi minus mu whole square plus n into x bar minus mu whole square minus 2n into x bar minus mu whole square, which is equal to summation I is equal to 1 to n xi minus mu whole square minus n into x bar minus mu whole square. That is actually summation xi minus x bar whole square. This is what has been written here. Summation xi minus x bar whole square is equal to summation xi minus mu whole square minus n into x bar minus mu whole square. Now, after deriving the sampling distribution for n minus 1 into s square by sigma square, just relate it with the chi-square distribution already studied and then derive the sampling distribution of sample variance. That is, it says suppose random samples of size n corresponding to some random variable x are drawn from a population whose size is much larger than n. Suppose also that x is normally distributed as a normal random variable with mean mu and standard deviation sigma greater than 0. Then n minus 1 into s square by sigma square is a chi-square random variable with n minus 1 degrees of freedom. We have seen when zi is a standard normal random variable with the mean 0 and standard deviation 1, then the summation of all such standard normal variable square becomes a chi-square random variable with k degrees of freedom. So, using that we have n minus 1 into s square by sigma square is a chi-square random variable with n minus 1 degrees of freedom. Let us see how this has come. So, we just find out the mean and standard deviation of s square. Mean and standard deviation of s square, as stated above, the expected value of s square is equal to sigma square, which is the variance of x. Therefore, mean of s square is sigma square. Now, we have n minus 1 into s square by sigma square is a chi-square random variable with n minus 1 degrees of freedom. Just imagine this chi-square random variable is having the mean as n minus 1. This is actually, if you would take it as k, then mean is k and standard deviation we have seen it is root of 2k. Here k is n minus 1, so root of 2 into n minus 1. So, it means n minus 1 into s square by sigma square has mean n minus 1. So, n minus 1 into s square by sigma square has mean n minus 1. Therefore, s square by sigma square has mean n minus 1 by n minus 1. N minus 1 goes to that side. Similarly, s square has mean n minus 1 by n minus 1 into sigma square. When you just cancel, we have s square has mean sigma square. That is, expectation of s square is equal to sigma square. This is proved. Similarly, discussing about variance and then we will derive the standard deviation. N minus 1 into sigma square has standard deviation root of 2 into n minus 1, isn't it? This is from the factor chi-square of n minus 1. Standard deviation is root of 2k. So, root of 2k is 2 n minus 1. It means n minus 1 into s square by sigma square has the standard deviation root of 2 into n minus 1. Okay, just cross multiply and then take the terms to the other side. We have that s square has a standard deviation root of 2 into n minus 1 by n minus 1 into sigma square, that has gone to that other side. Okay. So, root of 2 into n minus 1 by n minus 1, 1 n minus 1 the root gets cancelled. So, root of 2 by n minus 1 into sigma square. It means that standard deviation sigma s square, standard deviation of sample variance is root of 2 by n minus 1 into sigma square. Based on this discussion, now we shall do this problem, that is the annual college SAT scores are approximately normally distributed. It is an entrance examination, right? SAT scores are approximately normally distributed with mean mu is equal to 500 and standard deviation sigma is equal to 100. If S square is a sample variance on the space of all random samples of 50 SAT scores, this is the sample size, 50 has been given, then prove that 49 S square by sigma square is chi-square of 49, approximately a random variable S square. Also find mean mu S square and standard deviation of S square, that is sigma S square. We shall work out this problem. Okay. What all is given in the question? Starting the solution. Given in the question, mu is equal to 500 and standard deviation sigma is equal to 100. Okay. We have according to the theorem n minus 1 into S square by sigma square is a chi-square random variable with n minus 1 degrees of freedom, and n is given to be equal to 50. Therefore, n minus 1 into S square by sigma square means 50 minus 1 is 49. 50 minus 1, 49 S square by sigma square is a chi-square random variable with degrees of freedom 50 minus 1, that is 49. So, we have 49 S square by sigma square is a chi-square random variable with 49 degrees of freedom. This is proved. Now, this has chi-square random variable has mean k, which is k is actually here n minus 1, which is 49, and its standard deviation is root of 2k, which is equal to root of 2 into 49. It is actually root of 98. That is the mean and standard deviation of 49 S square by sigma square. Now, you are asked to find the mean of sample variance S square as a separate random variable and standard deviation of sample variance as a separate random variable. Mean of S square is sigma square and standard deviation of S square as a separate random variable is root of 2 by n minus 1 into sigma square. Okay. Therefore, mean of S square is equal to sigma square. Sigma is 100, therefore sigma square is 100 square, and the standard deviation of S square is equal to root of 2 by n minus 1. N is 50, 50 minus 1 into 100 square, which is approximately 2 by 49 into 100 square, which is equal to 2020. Hence, we have found out sigma S square and mu S square. Okay. Mu S square is 100 square, which is 10,000, and SD standard deviation of S square is 2020. Now, we shall work out this problem where the population is directly given. You have to draw the samples of size 3 and it is also drawn without replacement. So, just you have to find out the sampling distribution of a sample variance. Using the sampling distribution for sample variance, determine the mean, use the probability distribution determined to compute the mean and standard deviation of the sample variance S square for random samples of size 3 drawn without replacement from the population 1568, and then it is shown that when sampling without replacement, the mean of the corresponding sample variance is n sigma square by n minus 1, where sigma square is the population variance taken from an equiprobable space and n is the population size. Verify the result for the population 1568, the same thing when samples of size 3 are drawn without replacement. This is actually subdivision 3 we have to verify. Work out this problem. Solution. First of all, we shall determine probability distribution of S square. Okay. 1568 is drawn. This is given S is equal to 1, 5, 6, 8. Random samples of size 3. Samples of size 3. This is sampling without replacement. So no repetition will be allowed. Okay. Random samples of size 3. Size 3 in the sense, just take the combinations of 3 numbers with 1, 5, 6, 8 without repetition. 1, 5, 6 is one combination, and then another combination is 1, 5, 8, then 1, 6, 8, next is 5, 6, 8. Okay. Then the x bar values, right? X bar value is 4 x bar, just add by 3. 6 plus 5 plus 1, 12 divided by 3, it is 4, and this is 14 by 3, and this is 5, and this is 19 by 3. X bar is required for finding out S square. S square is xi, summation xi minus x bar whole square. Okay. It is calculated. Just do one calculation here and just write down the other values there in the tabular column. Okay. First of all, for 1, 5, 6 corresponding S square value, corresponding S square is calculated as S square is equal to summation xi minus x bar whole square. Summation I is equal to 1 to n. Just take 1 minus the corresponding x bar in the 1, 5, 6 combination is 4, right? So 1 minus 4 whole square plus next 5 minus 4 whole square plus 6 minus 4 whole square, which is minus 3 whole square plus 1 square plus 2 square. Okay. Actually, S square is summation I is equal to 1 to n xi minus x bar whole square by n minus 1, right? So the whole thing divided by n is 3. So 3 minus 1, which is 9 plus 1 plus 4 by 2, which is equal to 14 by 2 equal to 7. This is by n minus 1. So this is 7. Okay. Similarly, you can calculate it for 158. This is 168, right? Similarly, you can just calculate it for 158, which is 1 minus 14 by 3 whole square plus 5 minus 14 by 3 whole square plus 8 minus 14 by 3 whole square. The whole thing divided by 2 gives you the answer 37 by 3. Similarly, this is 1 minus 5 the whole square plus 6 minus 5 whole square plus 8 minus 5 the whole square. The whole thing divided by 2, which is equal to 13. Similarly, this is 5 minus 19 by 3 whole square plus 6 minus 19 by 3 whole square plus 8 minus 19 by 3 whole square. The whole thing divided by 2 gives you 7 by 3. This is actually S square value. The corresponding probability of S square is, here you are having 4 values, 7, 37 by 3, 13 and 7 by 3. 7 is appearing 1 times out of 4 possibilities, therefore its corresponding probability is 1 by 4. This is also 1 by 4, and since it has come from an equiprobable space, the probability will be equally distributed. Okay, this is the sampling distribution. This particular part is the sampling distribution of S square, or the probability distribution of S square. Okay. Next, you are asked to find out the mean of S square and the variance of S square. The mean of S square is taken from, I will just write S square values is 7, 37 by 3, then 13, 7 by 3. The corresponding probability P of S square is 1 by 4, 1 by 4, 1 by 4 and 1 by 4. For calculation of mean of S square, we want S square into P of S square value, which is 7 by 4, then 37 by 12, 13 by 4 and 7 by 12. Okay. So that we have mean of S square. Mean of S square is summation S square into P of S square is 7 by 4 plus, just add this 37 by 12 plus 13 by 4 plus 7 by 12, which is equal to 104 by 12 is equal to 26 by 3. That is the mean of S square. Next, to calculate variance of S square. Variance of S square is each value is subtracted with 26 by 3 whole square. Each xi is each value of sample variance is subtracted with its corresponding mean. The corresponding mean is 26 by 3 and each value is here 7 minus 26 by 3 whole square. The next value is 37, 37 by 3 minus 26 by 3 whole square. The next value is 13, 13 minus 26 by 3 whole square plus next value is 7 by 3 minus 26 by 3 whole square. Corresponding probability also has to be multiplied, right, because it is a summation x minus x bar whole square into the probability. Actually, variance is calculated as expectation of x minus x bar whole square. It is if you take s square as the variable, then s square minus mu s square whole square. It is summation s square minus mu s square whole square into its corresponding probability. So, into 1 by 4 has to be multiplied here with each thing. That gives you 676 by 36, which is equal to 169 by 9. That is the variance. So, hence we have just calculated mean of s square is equal to 26 by 3 and variance of s square is equal to 169 by 9. So, that standard deviation of s square is root of variance of s square is equal to root of 169 by 9 is 13 by 3. Also, one more thing is been asked to discuss. What is that? Third subdivision goes as we have finished with two subdivisions. You are asked to find out mean and standard deviation of sample variance and you are asked to find out this probability distribution of sample variance. It can be shown that when sampling without replacement, the mean of the corresponding sample variance is mu s square is equal to n by n minus 1 into sigma square, where n is the population size. Now, we have to verify the result for this population, where the population size is 4 when sample sizes of size 3 are drawn without replacement. You are asked to verify the mu whether mu s square is equal to n by n minus 1 into sigma square. This is actually population variance. This is calculated using the values of 1, 5, 6, 8. Just calculate it using each is taken as xi, then take xi minus x bar, then this is written as xi 1, 5, 6, 8 and its total is taken 20 by 4 which is 5, x bar is 5. So, xi minus 5 is taken minus 4, 0, 1, 3 and then xi minus x bar whole square is taken. Like that the variance is calculated here. The variance is xi minus x bar whole square is 16, 0, 1, 9. Like that it is calculated along with its probability. Its probability is 1 by 4, 1 by 4, 1 by 4, 1 by 4. Then it becomes this is probability of xi minus x bar whole square. Therefore, a population variance is a summation xi minus x bar whole square into corresponding probability xi minus x bar whole square, which is equal to 16 by 4 plus 0 into 1 by 4 plus 1 into 1 by 4 plus 9 into, isn't it, 9 into 1 by 4, which is equal to 26 by 4. This is your sigma square value. Now, therefore, to verify mu s square is equal to verify mu s square is equal to n by n minus 1 into sigma square. N is 4 by 4 minus 1 into 26 by 4, you have 26 by 3, that is mu s square is 26 by 3, which is same as the value which we have calculated. In this session, sampling distribution of variance is derived using the discussion of chi-square distribution done in the previous session. Also, a problem is worked out in determining the sampling distribution of variance for a population without replacement, and a mean and standard deviation of variance is also found out using the sampling without replacement and using the population as an equiprobable space. So, based on the discussion in this session, the following question may be posed. Suppose samples of size 10 corresponding to a population random variable are drawn without replacement. Suppose also that x is normal with mean 75 and standard deviation 5. What are the mean mu s square and standard deviation of the sample variance s square? Mu s square, you use it as a sigma square, and standard deviation of a sample variance use the formula of a sigma s square and then determine using the given values. Mu is given to be equal to 75 and standard deviation sigma is equal to 5. So, we can find out this. Derive the sampling distribution of variance using chi-square distribution. Thank you.